Okay, thank you, Marco. So yes, I will keep this light and relaxing. So the tutorial will be more presentation style and hands-on style. Still, I will do a few demo in front of you, and we can check a theorem. There is a theorem that says that when something has been working 10,000 times on your computer, when you show it to an audience, it stops working. So we will test this with various cases. Still, you are welcome with your computer to try to install the code when I will talk about installation, to try to run the same notebooks as me, etc. Okay, so CLASS is a code that I've been developing since 2009 with massive help from Thomas Tram since 2011 and from Niels Schoenberg till 2018. You see here the old CLASS logo, which is fine for a t-shirt, but a bit complicated, so we have a lighter logo. If you are fans of CLASS and you like it, come to me at the end. I have some stickers that I can distribute. Okay, so where does CLASS live? So it lives in several places. It's an actual Python module which lives somewhere on the PyPy repository. But the code is physically located on a GitHub, class public. Well, there is a class private, of course, but the one you can see is this one. It contains a master branch that most of you would be using. There are also a few other public branches. I will mention this at the end. And there is also the old-fashioned class web page, which contains a code as a .tar.gz that you can also download. And this page is still useful because it centralizes all the information about where is there some documentation, where can you find some wiki, what are the articles on which the code is based. And more importantly, this is the place where we explain all the little changes between different versions. So it's still an important place for class users. So there are documentation in many places, and I flash a few of them. What you need to know the most is just what are the name of the input parameters and what is syntax and what do they mean. And for this, there is a reference file, which is explanatory.ini. This is the only reference explaining the list and the meaning and the definition of all the input parameters. So you download it when you download class. If you just pip install class from PyPy, you won't get it. So then maybe you want to download class from GitHub or from the .tar.gz in order to get at least the explanatory.ini. So we tried different styles for documentations. People were always a bit unhappy with them. Now there is a new thing. Niels Schoenberg is developing and has almost finished Read the Docs that you can see here. And Read the Docs is really a nice format. It's something that many people like. So we hope that this version of documentation will make people happier, and you can already use it. I will flash a large language model agent that we have released. There will be a couple of slides on this. I will try a demo also. This is an AI that can help you to solve your class problem. I will show you. The classy wrapper has its own documentation in the form of doc strings, and there is an update here because many doc strings were missing until this summer, but in the minor release that I just did at lunchtime today, now all the classy functions have some nice doc strings. They are all well documented. There is also a manual which is generated automatically by Deoxygen that you always find when you download class. When you download class, there is always a repository called doc, and in this doc you find a PDF manual. And the HTML version of this manual is also living on the web and can be accessed if you look at the GitHub page or at the old-fashioned page. You will find the link to this automatic documentation. This wiki gives you more details about installation, and there are also courses on class with even exercise sheets. So there is many such course with links accessible from classcodes.net. They point you to my webpage, and in the course section of my webpage, there are many courses. Niels Schöneberg has some courses here. I will add some recent course that has been written by Markus Mosbeck, a postdoc in Aachen, and with this you have a lot of material. Okay, so I will talk about the overall architecture of class. Okay, can I do something about this? Yes, could even remove it completely with this. Yes. Okay, it's not perfect, but it doesn't matter. This I think I cannot control. Okay, I'm going to present here the overall architecture of the code. So the important part of the code lives in a series of main modules. I list the first one here. There will be a slide where I will give you the full list and I will tell you what they do, to which physics do they correspond. But you can guess from the name: background, thermodynamics, perturbation, Fourier transfer, etc. And these modules are sequential. They only need to be evaluated once in a given order. They have a linear dependency. And so executing class means going through each of these modules. And they are written in C. C is really fast. You know, if we would write all this in Python, the code would be considerably slower. So it's better to write a C code and then wrap it from Python. And we choose plain C for different reasons. We can argue between C and C++. There are advantages, inconvenience, things about speed, things about robustness, etc. What is nice with C is that it's easier to understand and we leave less people on the side by adopting plain C. But at some point we realize that we want a bit of C++ because our parallelization was using OpenMP. And OpenMP is less and less supported. On many computers, it's becoming painful to install OpenMP. So at some point, we said, okay, for our parallelization, let's forget OpenMP. Let's go to the native parallelization style of C++. And it means that in some module, you have some C++, but only for the parallelization. And that's no problem. It just means that some of the module needs to be compiled by a C++ compiler, and the other one by a C compiler. There is very good compatibility with C and C++, so you can compute your different modules, some with C, some with C++, and assemble them at the end. This is no problem. Of course, if you are only an end user and you want to use class from Python, you will not even need to know about this. This is just for the coding fans. Okay, so in the main module, we put the task of a typical Einstein-Boltzmann solver. And sometimes there are auxiliary tasks on which we consider that maybe we are not specialists, or these tasks are really independent from the rest. And then we put them in another directory, which contains the external modules. So I give here only a few examples because there must be something like 10 external modules. So HM code or HaloFit contain these fitting formula for nonlinear corrections. BBN actually would solve, ideally would solve BBN with a fast code like the one of Hong Wang, but in fact it's just reading an interpolation table produced by another BBN code. And I'm going at the end to talk about the OneLoop module, which is between brackets because unfortunately it's still not publicly released. Okay, so when you compile C, or even when you pip install CLASS-C, the first step is the C compilation. The C compiler or C++ compiler looks at all this stuff and it produces two things, a library and an executable. The library will be very useful if you want to use a Python wrapper. The executable is in fact all what you need if you are not a Python fan and you just want to run your code in the old-fashioned way in a terminal by giving to the code an input file and by expecting to find your results written in output files. We have been doing this for a while and we are still maintaining this option. This option is nice because sometimes you want to modify class. When you modify class, you will need to do some debugging. And if you do the debugging directly at the Python level, you will suffer. It's much better to write your modification, stay at the C level and use the C executable to check that your code is working. And when it does, then you check that it's still compatible with the Python wrapper. So the C executable is still a nice tool. Then the next step in the automatic compilation is calling the Cython compiler. So Cython is a level of language between C and Python, ensuring that you are allowed to embed some C code into Python, but it needs a compilation step. It's not like plain Python, which is not a compiled language. With Cython, you need to run a compiler at some point. This compiler will just read the library. It will not look directly at these files. And it will read also something that is called classy.pyx, which is the Python wrapper, the things that we wrote and that you may want to modify yourself. And in these classy, there are calls to the C function, which are identified from the library. The Cython compiler puts everything together and produces a Python module, which is just called classy. And then you can use classy in the usual way by calling some Python script or notebook. You import classy, and then you have access to all the class functions. And then your results will be written in some classes, and you can directly make some plots, etc. Okay, so how do you install class or classy? You have the choice. So suppose that you are a basic user. You only want to use the code in Python. You are not interested in modifying it. Then the easier is to do just a pip install classy. And then this will fetch the code from the PyPy repository, which is somewhere, I don't know where, and it will just install it on your computer. So this is the easiest, and if you want to do it now, feel free. I've just been aware of something because I got an email from this postdoc, Marcus Mosbeck, a couple of hours ago. So usually when you install a module, it will install the proper dependency. And so when we define the classy installation routine, we said, okay, before installing classy, check that the user has NumPy and SciPy and Cython, which are the three important modules that classy uses. And it turns out that we realized that we didn't write this dependency in a robust way. So maybe some of you who have not installed NumPy, SciPy, Cython before will get a complaint. But not all of you. For some of you, it will work. It's a platform dependent. So if you get a complaint, you should first install these three modules, and then you pip install classy again, and it should work. And we know how to fix this. It's a very small fix, and we will do it as soon as possible. Okay, but maybe you want the code to be living in a definite place on your computer where you can look at it, you can look at explanatory.ini, you can look at the documentation, and maybe you can modify the code yourself. And then you would get it from GitHub or with a .tar.gz, and you would want to enforce the installation of this version in a given place of your computer. Then you go to the class directory, you pip install dot, and you are sure that pip will fetch classy from this place on your computer and not from PyPy somewhere on the web. And what you could do also is you are only interested in the C code or you are in debugging process. You don't want to waste time because the full compilation is long. You only want to compile the class executable from the C code. Then using the traditional makefile style, you go to your directory where class has been downloaded, and you make class. -J, will make it faster. It will be compilation using all your cores. And finally, if you would make -J all, or just make -J, then it would do everything, and it would be actually equivalent to pip install dot. So it does the same, but instead of using pip, it uses makefile. So all these things are supposed to work. If you have a problem, let me know. We can try to sort it out. Okay, assuming that you have installed the code and that you have never used it, the minimum you need to know is that if you want to do an old school run of the C code, You go to your directory, you stay in your terminal, and you /class with the name of an input file. And when you download class, you download it with this monster file called explanatory.ini, which I recommend never to change. It should be for you, it should be a reference. You leave it untouched, and when you want to remember the syntax of a parameter, you look at this. Typically, you want to run with a much lighter file, and for instance, when you download class, you have a default.ini. It's only a few lines. It will only define the important parameters. The other one will be set to plain default value, and that's all what you need. Okay, so you /class default.ini, and on your terminal, you will get some nice information. When I use the code from Python when there is a good reason, but if I want something simple, the C code is nice because on the terminal, you get a lot of information. You can check in your universe what were the characteristic times, the characteristic scale, you get some nice outputs on the terminal, and then in the files, you have the results of the calculation. Okay, but if you want to use the code from Python, then you have the choice between writing a Python script or a notebook, and it's not nice to write this from scratch. So when you download class, you download a dozen of examples of notebooks and scripts. And our hope is that what you want to do will look a little bit like one of our scripts, so you can start from there and you can customize it instead of writing everything from scratch. So the list of scripts and notebooks that we provide is completely identical because in fact we developed the notebook and it's an automatic process that generates the scripts. So you are sure that they match each other really very at 100%. So you can use whatever. I'm going to walk with you through the step of the simplest starting script, which is called warm-up. We will do this in a few seconds. So as I said, the exhaustive list of all input parameters is in explanatory.ini. Also for us, we consider that a parameter is official when it's there. It's really the place where we define all the parameters. And so for each parameter, you have a name. And if you use the code from a terminal, the C code from a terminal, you pass an input file where every line is name equal number or string. If you are in Python and you have created your class containing class, you set parameters with a dot set and then passing a dictionary. And so in this case, the style is the one of a dictionary with a name between brackets, column, and the number or the string. Okay, and now I will do my first demo with warmup.ipynb. So for those who are familiar with class, it will sound like too easy, but I will show you some more recent and more advanced stuff later on. Okay, so I'm going probably to share my desktop instead now. So I move here. Yeah, for some reason I cannot share the whole window anymore. I don't know, so I will share just a notebook. So you cannot see it, but first I pip install dot to be sure that on my computer I pip install the last version of class. And while the code pip install dot the code, I share the notebook. And probably you want me to make things a little bit bigger. And to make it bigger, okay, command plus did not work. So is it big enough? It's a bit small. Yeah, now, okay. Okay, so yeah, so Class C is installed and I import it. Usually when you import it the first time after a new installation, it's very slow. That's not us, it's because it needs to look at all the dependency and settle everything. Okay, it was not too slow. Okay, so now I want to create an instance of the code. So this will be my instance, and this is where we will put the input, the output, and so typically it will account for a given cosmology. And in this example, I want to simulate a lambda cosmology, so I open this instance of class. You could open many of them at the same time in the same notebook. You could have 100 models. Okay, and then I want to define some typical input parameters. So I choose to write my dictionary independently, and then I will pass my input parameter by saying that my cosmology is set to this dictionary. You can do it in one step or in many steps, it doesn't matter. So here you have your lambda CDM parameter, and I'm giving precisions about neutrinos. Here I have one species of massive neutrinos with a mass of 0.06 electron volts and the standard temperature. And I have two species of massless neutrinos, and this number is such that the total number of effective neutrinos will be the usual 3.044. I could use another syntax. I could do this, and it would work exactly the same. The code would know that it would need to take this number, remove the contribution of massive neutrinos, and consider what remains as massless neutrinos. So I go back to the previous number. I forgot what it was exactly, doesn't matter. So all the syntax is explained in explanatory.ini. This is baryon, this is cold dark matter, this is ultra-relativistic species, and this is non-cold dark matter. For us, massive neutrinos are a particular case of non-cold dark matter, but there are many others. If we would deal with axions or with warm dark matter, they would enter in the category of non-cold dark matter. And here we say what we want to compute. In this example, we want to compute the matter power spectrum, the temperature CLs, the polarization CLs, and the lensing potential CLs. And we want also to include CMB lensing correction. You could say, oh, is this redundant with passing LCL? No. LCL says compute the CMB lensing power spectrum. And lensing equal yes, say use this information jointly with information on the unlensed temperature and polarization to compute the lensed temperature and polarization spectra. PK will be computed up to a Kmax of 1 H megaparsec, and here we want halofit to get some nonlinear corrections. So we set our input. Let me execute the cell. Okay. And then we need to retrieve our information. In all versions of class, you always had to go through a step called .compute. .compute was really the place where you would run the C code. All the results would then be stored inside your class, and you could retrieve these results one after each other. Now we decided to skip this step. When you directly ask for some output, the code will say, did I run? If yes, information is there, I retrieve it. If not, I run and then I retrieve it. So you don't need to use .compute anymore, unless in special cases when you want to tell the code to run, but not to output anything. Okay, so here I'm going, of course, to get all the length CLs. This will be stored in this array as a dictionary. And since I would tend to forget the syntax of this dictionary, I ask for the keys of the dictionary. So I run it, and now CLs is a dictionary with keys corresponding to the different spectra that you see here. The last one, L, using the LaTeX syntax, is a multiple number. Here I have my multiple for temperature, polarization, the cross mode, etc. You could say that this command here was strangely concise. I didn't say if I wanted the E mode, the B mode. I didn't say if I wanted the cross correlation or not. So the thing is that the input module of class is kind of smart. It will always try to make sense of what you ask. It has an interpretation layer. And for instance, when you say I want polarization, The code knows that if you have scalar mode, you only want the E mode, and if you have tensors, you want both. And the code will always try to compute all the available quantity given your input. So now I've put temperature and polarization. So the code knows that it should compute CLTE, and it also knows that it should not compute CLTB because TB would vanish. So it knows all this. You don't need to be very precise. And as a matter of fact, it has computed TE, EE, TE, BB, and also the cross PP, which is a CMB lensing, and another quantity which is non-zero and potentially interesting is a cross correlation of CMB lensing with temperature. P is the first letter of phi. Phi is a lensing potential. Of course, if you forget all this, you want to check the syntax in the documentation. And you can open CLASS-C to see the documentation, but of course there are many other ways to do so. I wanted to open a new window. Ah, yes, here it goes. So just to show you, if you have forgotten the syntax, you have automatic completion. Like you can type lambda CDM, and you remember that it starts with CL, but you don't remember the rest, so you tab. Ah, no, sorry, length. You tab and you see all the functions starting by length. And the theorem is working because normally when I tab here, I get automatic completion with all the possibility. Now, because you are there, it's not working. I don't know why. So I will put the full name, and at least I will put a question mark after, and I execute the cell, and at least this returns the documentation of the function. And since we worked on this summer, I can guarantee that for any existing function, you will get a nice documentation with explanation of all the parameters, of the input format, output format, units, etc. It's quite detailed. And you see, for instance, what would be the name of the possible keys here. Okay, anyway, we have now our CL stored there, and we want to plot them. So now it's a piece of cake. I extract from my CL the multiples and the CLTT and the CLEE, and this is used to say that I want to start at the quadruple. Okay, so now this is in arrays, and I want to plot. And so I will plot L and CLTT, and usually we always normalize CLTT by LL plus 1 over 2 pi. This is what you see in any plot of the CMB spectra. I did not have time to explain one in the lecture. It's a bit technical, but there is a good reason. Okay, we get our CLTT plot, and the same for CLEE. Okay, and now we want to plot the matter power spectrum. So here the syntax is a bit different. The code wants first to know what are the values of K at which you want the matter power spectrum. So you have to define it yourself. So I create an array of logarithmically spaced values of K. I retrieve H directly from my cosmology because I want to use small h to make conversion of units between megaparsec and megaparsec over H. Class, by default, wants to work with units of megaparsec to some power without the h. There are a few functions where you can ask the code to use everything in units of megaparsec over h. But I'm using here this function getPkAll because depending on the argument you pass, it would give you all the kind of pk that you have computed. Here I don't pass any argument, so by default it will give me the nonlinear matter power spectrum and just this. But there are many other options. And so this function, as you could check by looking at the doc, this function expects a list of wave numbers in units of h by megaparsec, and will give you the pk in units of megaparsec to the 3. So if you wanted these k values to be in h by megaparsec, you need to correct for it. And if you want your matter power spectrum to be in megaparsec over h to the 3, you need to correct for it here. So this is unit conversion. Okay, I run, and now I can plot my power spectrum by plotting just this. And we see immediately that it's a nonlinear matter-power spectrum because at the beginning we see the BAO, we see a smooth slope given by k to the ns minus 1 log k squared as shown by Misha. But here very clearly we see an enhancement. This is a nonlinear correction, which is in this case was computed by Halofit. So this is how a minimal module works. And you can tell me already if you have questions on this before I go on. Yeah. Yes. Very nice. Okay. So the code calls the sequence of module. In background, it computes homogeneous cosmology. Thermodynamics, it computes the thermal evolution. Perturbation, it computes the perturbation. So there are different levels. And depending on the output you want, you need to run all the modules or a fraction of them. So before we were calling always .compute. The code would go through all the modules and would evaluate all the ones needed given the input parameters. And then you would retrieve your quantity. Now what it does is, if you have skipped the .compute, at the beginning it has not run. And suppose you ask for a background quantity to say, oh, I need not start to run, but I need to output a background quantity. So it will run the background module only. And it will stay there, and it will give you your result. And later on, you ask for the CLs. It said, oh, I started the run, but I didn't go far enough. So we'll complete the run up till the step where the CLs are computed, and it will stop there. And it can do this sequentially as much as you want. No, you can call it. If you are used to it and you don't want to change your life, it's perfectly fine. Yeah. But so now when you download the class since today and you get the default notebook, they don't have a .compute anymore. Maybe except one or two, I'm not sure. Yes? Yeah, you are only limited by time. So if in your input, you don't say that you want to go to a high Lmax, and then you try to retrieve the CL at a higher Lmax, it will complain. You need to pass in your input. So by default, there is a parameter called Lmax scalar. It's written in explanatory.ini. And by default, this parameter is set to 2500. If you know that you want to go beyond, you have to pass Lmax scalar equals, say, 6000. And then you can retrieve the CL with length CL at any L up to 6000. But indeed, what you use in the retrieval function should be smaller than the Lmax that you have set in input. Okay, if there is no other question, I come back to the main presentation. So, I come back here. And so I showed you what the warm-up module does, and what I hope is that for many of your applications, you would find an already existing notebook that would be your starting point. So I show you what is the output of the most useful notebook, and you will see that many of them are things that you have seen in the lectures before. So for instance, this notebook CLTT terms shows you how to decompose the total temperature spectrum in its different contribution. CLST is the one showing all the spectra for temperature and polarization of scalar and tensors. And then very often, one thing which is useful for you or for directly putting in your paper is to show the variation of an output quantity, CLs or matter power spectrum, when you fix all parameters but one. And we have two examples of this, varying P annihilation and varying NF, doing plots like we have seen in the lecture, but for other parameters. In this case, this is the absolute dependence of CLTT on P annihilation, so the dark matter annihilation parameter, which has been described in the BSM course. And in this case, you see the relative variation, so with respect to a reference, of CLTT when you vary the neutrino effective number, the effective number of neutrino or relativistic species. And I think in these modules, you find also how to get the sign for the matter power spectrum. So starting from there, you can adapt it to your favorite parameter, or maybe you have modified class for new physics and you want to check what is the effect of a parameter that you define yourself. You can start from these notebooks and make a nice plot for your article. Okay, test HM code shows how to use HM code, but also HaloFit. Here it gives you the linear power spectrum, the nonlinear power spectrum, and different version of a de-wiggled power spectrum obtained either numerically or analytically from the Eisenstein NU formula. This shows you the residual of some power spectra for different values of the total neutrino mass, but you assuming normal versus inverted hierarchy. This one shows you how to plot just background quantities. In this case, it's the plot of the luminosity and angular diameter distances. You find the same plot in the Dodelson book on modern cosmology. And actually, the second edition of modern cosmology gets many of its plots from CLASS. And I even helped a bit Fabian Schmidt to produce them. So CLASS is like the official code of modern cosmology by Dodelson and Schmidt. In this module, thermodynamics, you plot the visibility function. Okay, that we also show that in the lecture, and you recognize these plots from the lecture: 1 time, 1k, many k. These are the name of the notebook that produce them, so you have access to them. Okay, now let's connect this to the physics that we have learned in the lecture. So, what about these main modules? So the first module, called input, reads the input parameter, but it's not just a stupid parser. It has some logic implemented. It checks whether your input is self-consistent or redundant or inconsistent. Are you trying to give the same information in 2 different units? Is it consistent? Are you trying to fix the tensor tilt while you did not require tensor? It will complain when you do something strange. And otherwise, when you don't do something strange, but you have not passed all the parameters, it will default to standard value of the parameters that you did not give. So there is a bit of logic. The input module knows a little bit about cosmology and can take decisions. The background module is in charge of just evolving the Friedman equation and other background quantities. And then at this stage, you could already plot distances as a function of redshift, for instance. Thermodynamics modules go through the thermal history, which means mainly recombination and reionization. But if you have some advanced model of dark matter, it could also simulate dark matter annihilation and how the exotic energy produces by, I don't know, primordial black hole evaporation will be distributed to photons and baryons. It will do all this stuff also for exotic models. And then you can plot, for instance, a visibility function. That would be an example. The perturbation module evolves a system of perturbations, but normalized to the adiabatic initial condition or other ones, like the one we did not describe, called isocurvature initial conditions, or any mixture of these. And because these are, it's computing perturbations normalized to a well-defined initial condition, in fact, what this module computes is what we called in the lecture, not a perturbation, but a transfer function. In particular, for adiabatic initial condition, all the perturbations that you would see inside the code are normalized to R equal 1. The primordial module computes the primordial spectrum, and if you use a parametric form, like for instance with a tilt, a power law with a tilt, and maybe a running of the tilt, this module will be extremely trivial and will take a few, I don't know, nanoseconds. However, this module can also simulate inflation. It can do a full numerical evolution of an inflationary model. It only works for single field inflation, but you can customize a potential and it will integrate the full Mukhanov-Sasaki equation to compute, in this case, the scalar and the tensor power spectra. The Fourier module takes information on the transfer function and on the primordial perturbation and assembles them to form all the observables which are defined in Fourier space, and in particular, the matter power spectrum. But for instance, sigma 8 can be computed also at this stage. Some observables require more steps. They require to go to harmonic space, and this is why there is a transfer module. And the transfer module computes all the transfer function that depends on a multiple L. So you could say, why don't you call this transfer and this differently? Well, historical reason. In the old days, what people call the CMB transfer function were always these ones, and we adopted this name, and we are not going to change now. But it means these are transfer function in Fourier space, and these are transfer function in multiple space. The next one, called harmonic, computes now the observable in harmonic space. So there the naming is consistent. The Fourier gives you the observable in Fourier space. The harmonic module gives you the observable in harmonic or multiple space, like the CMB-CLs, but also the large-scale structure CLs. Okay, CLASS will compute for you the CLs of weak lensing, of galaxy number count, and all kinds of cross-correlations. The lensing module is not doing weak lensing. Weak lensing is handled by the harmonic module. It's doing the lensing of the CMB specifically. It's doing what I described this morning as a complicated convolution between the unlensed CLs and a smoothing kernel to give you the lensed CMB spectra. The distortion module is doing what we did not describe in the lecture. It gives you, for a given model, it evaluates the CMB spectral distortions. And you can run it in a simplified form where it will just give you a Y and a mu distortion. But you have the option to go beyond and to compute the full phase space distribution of the photon in a given model. It can be in a simple model, or it can be a model with some exotic energy release that would lead to some non-trivial spectral distortion of the black body distribution of the photons. All right, so in the external module, some external modules are a bit trivial. They just contain some interpolation table. Like I told you, the BBN module is not a BBN code, but an interpolation table. The distortion module contains a huge interpolation table computed by Jens Schluba, which allows us to easily get the CMB spectral distortions without solving very complicated equations like the Campanitz equation, etc. Then the other one contains some actual code specialized on some aspect. So HiRec is a code we use by default to simulate recombination from Nanun Lee and Yassin Ali Aimut. You can Breakfast is another recombination code that we adapted a bit, and you can switch from one to the other. For your nonlinear corrections, you can trust HaloFit or HM code. Of course, what is nicer is to use EFT of large-scale structure. I will come to this. Heating is a module which allows you to have some non-trivial mechanisms of energy injection accounted by the code. Things related to dark matter annihilation, to primordial black hole evaporation, to black hole accretion, with energy transfer producing various effects. External PK is when you are an expert of inflation, but your model of inflation is too complicated to be solved by CLASS itself. Maybe you have multiple inflation, you have your own code, and this would be an interface between your own code and the primordial module, such that your own code is computing and passing on the fly a primordial spectrum. Real space interface is something that I will show. I think it's the next slide. Yeah, so this is just for fun, for impressing your little brother or little sister with an animation of CMB physics. So I will try to run it for you. It has been developed by bachelor students in Aachen, very good ones in their bachelor thesis. Okay, and it's just for pedagogical purpose. So it's going to show you a small movie of the evolution of linear fluctuations in a little region in the universe. So you could try to explain linear theory just from this, but it's not enough. So first I show you, since I cannot share my whole window, which is really silly, new thing, I will share first a terminal, and here I have a version of class, okay, which is installed in this directory. And inside class is installed, you recognize source, where the main module are installed, notebooks, where you find all the notebooks, scripts with all the Python scripts. This Python thing contains a Python wrapper. There are also many files that I added and that you don't have when you download, doesn't matter. But now I will go to external. Yeah, you can see. I go to external. In external, I have all these external modules that I mentioned, and I go to the real space interface. And there is a README. I always forget what needs to be done before launching this interface. So we check here that, okay, we need to install some module. Probably on my computer, it's okay. Then I need to run a Tornado server and to paste this address into my browser. So I will do exactly this. I launch this Tornado server, which will make my browser talk with class. And then I will paste this address in my browser. And then we have a second occasion to check our theorem. Will it work? We shall see soon. In my case, it's Safari. I paste this URL. Okay, and it opens a nice window with lots of comments. I will show you a bit all the functions later on. Okay, so far, nothing, because we have not set up initial conditions. Whew, that's asking a lot. Yeah, I can. Yeah. Okay, there are lots of buttons. It takes time to get familiar with them. Here I could choose the size of the box I want to, it's not a box, it's a slice. The size of the slice I want to simulate, and it's not an n-body simulation, it will use only linear theory. So I choose the size of the slice I want to visualize and the resolution. I will stick to default. I can configure